Hi, y'all. So if you have watched prior videos that I've done on this particular chapter, on the force chapter, or you have sat in my class, physically, actually face to face, you might have seen this slide before. This is my steps for force problems, and this is in general. It doesn't always apply, but it's a good general rule that when we're faced with force problems, our first step is to draw a free body diagram. To define our X and Y directions based on the forces that exist in the free body diagram, to break any forces that aren't pointing in either the X or Y direction up into X and Y components, and then to apply Newton's second law in the X and Y directions. So we're going to take that set of steps and apply it to this particular problem. This one says that we've got a skier on a ski slope, and that slope is at a 20-degree angle with respect to the horizontal. We're given that the skier's mass is 50 kilograms. We're asked to find the normal force the ground exerts on the skier and the skier's acceleration. And we're also asked to, and we're told that the snow exerts a frictional force of 54 newtons on the skier. All right. So our first step here is just going to be to try to actually draw a free body diagram. And let's see, before we do that, maybe just do a little picture of our skier. There we go. And a free body diagram is just a dot, there we go, with forces drawn in that represent the different interactions between the skier and the outside world. Now, the first force we can think about is of course gravity, weight that the earth is exerting on the skier. What else is going on here? Well, we've got the normal force that the ground is exerting on the skier, as well as a frictional force, there we go, that the ground is exerting on the skier. All right, so there's my free body diagram. So that's step one. Step two is to draw out X and Y directions for this particular problem. So our skier is going to tend to go down the slope. So I'm going to make down the slope my X direction and perpendicular to the slope my Y direction. Anytime we've got motion in one set direction, we definitely want to make that direction of motion one of our cardinal directions, either X or Y. It just ends up, the math ends up working a lot easier if we just have motion in one direction rather than motion in two. All right, so that's step number two on our list of steps. Step number three was to break any forces that don't point in either the X or Y direction into X and Y components. So I look at the normal force. The normal force absolutely is pointing in the Y direction. The friction force is pointing along the X direction. The weight force is the only force that's not pointing in either X or Y. It's an oddball, so I need to break it up into X and Y components. The way that I do this is I just start on my dot that represents the skier, and I draw backwards from the normal force. There we go. I draw backwards until I get to the point where I'm just about parallel to my friction force, so that I can draw a nice parallel line there along in my X direction to complete my right triangle for my weight. Okay, let's erase maybe my drawing. There we go. Okay. All right. And then let's see here. There we go. Okay. All right, so I've got the W sub Y and W sub X components of my weight force drawn in. And we can see that W sub Y, it points along the Y direction. W sub X points along the X direction. And in order to figure out the actual values of those, I would need to know the value of one of the angles in that weight triangle. We're told that the slope here in this particular problem is a 20-degree angle, and that slope is going to be the exact same as that angle at the apex of my weight triangle. Yeah, I know it's a little sloppy. I'm doing the best I can. With limited resources, mainly drawing with my finger. All right, so let's see. We can do a little analysis on this weight triangle. Cosine of 20 degrees is going to be equal to adjacent over hypotenuse. That's W sub y over W. This leads me to, if I solve this for W sub y, the relationship that W sub y is going to be equal to W times the cosine of 20 degrees. All right, if cosine gives us the y component, then sine is going to give us the x component. There we go. And at this point, I've completed step 3 of my process. I've broken my my forces into x and y components. Those forces that don't just solely go in x or in y. All right. Step 4 is to apply Newton's second law in the x and y direction. So we'll go ahead and do that. And let's see. I want to clear everything, and we'll give ourselves a little bit more space here by proceeding on to the next slide. If I can get that active, there we go. And so I will, let's see, apply Newton's second law in the x and y directions. All right, so we'll start out just with the x direction. Okay, the sum of the forces in the x direction is equal to mass times acceleration in the x direction. Well, if I look back at that free body diagram, maybe, I don't know, go back half a minute in the video or something like that. If I look at that free body diagram, I can see that the x component of the weight force is pointing in the positive x direction, down the slope. And the frictional force is pointing in the negative x direction, that's up the slope. So friction is going to resist that x component of weight. W sub x points in the positive direction. F points in the negative x direction. That's why I've got the negative sign in front of the F. And let's see, I can fill in here W sine of 20 degrees for my W sub x minus my frictional force is equal to mass times acceleration in the x direction. Okay, awesome. And now I can go ahead and fill in what is W? W is mg, weight is mass times gravity. There we go. And now I could go ahead and grab numbers for everything. So we'll see if we can do that. We'll see if we can do that. Okay. I forgot the numbers. So let's see here. We have 50 kilograms for the mass. G is 9.8. We've got the sine of 20 degrees. The friction force is 54 newtons. That was given in the prior slide. The mass is 50 kilograms. And then I've got the acceleration in the x direction. All right, so if I plug the numbers on the left-hand side of that equation into a calculator, I will get out the result. At least eventually I will get out the result. That 114 newtons approximately is equal to 50 kilograms times the acceleration in the x direction. Okay. So if I go ahead and divide both sides by 50, I get out that my acceleration is 2.27 meters per second squared. So that's the acceleration of the skier as they go down the slope. Yeah, so we've got that. Okay. The question also asks for the size of the normal force that the slope exerts on the skier, or that the ground exerts on the skier. So we can go ahead and do that one. Let me clear all this. Okay, there we go. And let's look at the sum of the forces in the y direction. Okay. So we can ask ourselves the question, well, is the skier going to move at all in the y direction? And we keep in mind that the y direction is perpendicular to the slope. That's what we said that, let's see, there we go. There's our skier. We said that x is this way and y is this way. And is the skier going to be moving in the y direction? Well, the skier is not going to be lifting off the slope, not going to be floating into the air, and the skier is also not going to be falling, through the slope. So there is no acceleration in the y direction. The acceleration in the y direction is 0, which means that the right-hand side of this equation is just 0. And now we can go ahead and we can take a look at our free body diagram, our normal, our friction, W, the fact that we've got a W sub y and a W sub x there. And we can take the information on that free body diagram and fill in on the left-hand side of this equation the forces that act in the y direction. All right, so what do we have? We've got a normal force that points in the positive y direction. And then that y component of my weight force points in the negative y direction. And those guys are going to sum to 0. By rearranging this equation, I can see that normal is going to be equal to the y component of the weight, whatever that is. And let's see, we figured out that the y component of the weight was equal to the weight times the cosine of 20 degrees. Weight is just mg. And I can fill in my numbers here and then evaluate those to figure out what my normal force is. 20 degrees, there we go. And this ends up being 460 newtons. All right, and that will do it for that problem. I've answered everything that we were asked for. So I'll stop this and maybe look at something else in another video.